Hello everyone. Here we're going to be talking about deriving the production possibilities frontier with economies of scale in production. So, we're going to recall the idea of the feasible set. It's a set of actions we can take given our economic, physical, and other constraints. Now, the production possibilities frontier, also called the PPF, is something that for two goods shows the maximum amount of one good that can be produced given output of the other good. The boundary of the producer's feasible set is basically what we want to think about here. That's what the PPF is. It's also an alternative name for the feasible frontier. Okay, so we're going to consider Alex, who can spend his time fishing and making shirts in some combination, including complete specialization, either making only shirts or only fishing. Now, for Alex, we've got the following few ideas. Basically, his labor time is bad. He would rather have less labor time. Okay. Now, the thing is he can work up to a maximum of 10 hours. Now, he prefers to have more of both shirts of fish. Both shirts and fish are goods. Okay, so that's in terms of his preferences. Now, the question is, how much time will he spend on getting these fish and shirts, things that he likes both of? Well, we're going to have to find MRS equal to MRT in order to find out how many of those two items he's going to consume. Now, the question then is, how do we get the MRT? We're going to have to find a production possibilities frontier for Alex. We're going to have to find it for the two goods, fish and shirts. And we're going to then have to find the MRT between fish and shirts, these two items that Alex likes. Okay, so in order to understand, to answer this question, how much time he'll spend on each activity, either fishing or shirt production, we have to have more information. Firstly, we're going to have to think about the feasible set of combinations of fish and shirts amounts that are available to him given his labor time, and the production functions at his disposal. Now that is going to end up giving us the MRT. So once I know how much time I can spend on shirts and how much time I can spend on fish and how I engage in the production of either of those things, those are going to result for me in the production possibilities frontier. Those are then going to produce this marginal rate of transformation of shirts into fish or fish into shirts. Okay. Now, the indifference map is going to represent his valuation of each of the combinations of the two goods. That's going to get us the marginal rate of substitution. Now, we've already looked at different ways of finding the indifference curves in Chapter 3, so we are going to look at this at another point in the textbook, but this video is only going to be dealing with the derivation of the production possibilities frontier. But the indifference curves, what would they give us? They would give us the marginal rate of substitution, and when Alex maximizes his utility, subject to the constraint of his production possibilities frontier, he would set the marginal rate of substitution from his indifference curves equal to the marginal rate of transformation from his production possibilities frontier. Okay, now in this video, we're only going to think about deriving the feasible set of combination of fish and shirts to get the marginal rate of transformation. Now, we're going to consider the following relationship. We're going to say that there are economies of scale in shirt making. So shirt making is a kind of manufacturing process. We're going to say as a consequence, there are economies of scale in production. So as you produce more shirts, it's going to cost you less time to produce a marginal shirt. That's the basic intuition here. Now, there are going to be constant returns to scale in fishing. So as you fish, the marginal production and average product are going to basically remain the same as you fish. Now, the production function for fish is going to be linear, and so the average and marginal products of labor are going to be constant, and both are equal. The production function for shirts is going to be quadratic for simplicity to represent this idea of economies of scale. Now, what that means is that the average and marginal products of labor are greater as more labor is dedicated to production. Okay, so those are our intuitions here about capturing this idea of economies of scale in manufacturing production, but constant returns to scale in kind of agricultural production. Those are the choices that Alex is making. So, firstly, we have the production function for fish. Now, what we can see here is we've got labor for fish on the vertical axis, and we've got the amount of fish that he can get on the x-axis. Now, that might seem like a little bit strange, but what we want to think about is that the labor for fish results in the production of the output of fish. You could also have done this on other axes, but you're going to see y in a little while. We've actually put x on the vertical axis. So that's the production of fish, with the amount of fish on the horizontal axis and then the labor for fish on the vertical axis. And what we can see here is as you're dedicating more time to fish, the production or the output of fish is increasing, but it's doing so at a constant rate. So constant returns to scale, dedicating half your time to fish of the total time means you get half of what he would have produced at 10 hours. Okay. At C, over here, he dedicates 10 hours to fishing for 5 fish versus point F over here, where he dedicates 5 hours for 2.25 fish. Now, 2.5 fish, not 2.25 fish. So notice here, what are we seeing? We're basically seeing just constant returns to scale, and just the amount of the production function here is x equals 1/2 of the labor time devoted to fishing. Okay, so that's the production function. Very simple linear production function. Now with shirts, what have we done here? We've got the labor for shirts on the horizontal, and we've got the amount of shirts on the vertical. You'll see why we've got that a little bit later. But what you want to think about here is that as you devote more time to shirt production, what is happening? You're getting more and more shirts. So at 5 hours of shirts, of labor dedicated to shirt production, you get 2.5 shirts. But if you dedicate 10 hours to shirt production, you get 10 shirts. Okay, and so what do we have there? The production function for shirts is quadratic. It's raised to the power 2, and it's basically 1/10 the labor dedicated to shirts squared. Okay, so if I dedicate 10 hours, 10 squared is 100, divided by 10 is equal to 10. If I dedicate 5 hours, that's 5 squared, which is 25, divided by 10 is 2.5. Okay, so when I think about this, we've got the economies of scale in shirt production. From dedicate half his time to shirts, gets a quarter of the output relative to 10 hours of labor for shirts, 10 versus 2.5. So at point A, Alex spends all his time on producing shirts, so he gets 10 shirts and 0 fish. So notice here, if he spends all his time on shirt production and 0 time on fish production, he gets 10 shirts and no fish. If he produced at point E, he would get 2.5 shirts. He would have 5 hours left for spending on fish production or fish catching. And then he would get how many? Well, if we go back, we can see he would have gotten 2.5 fish. Okay, so we've got those ideas in mind here. So when we think about this, the reason that we can talk about him dedicating the amount of time to these different activities is, notice here, I've got labor for shirts on the horizontal axis. I've got labor for fish on the vertical axis. Remember why we had those on those two axes earlier. And what I can see here is that I've got the feasible set of hours here shaded in green. And so I can spend anywhere up to 10 hours on the two activities. And so the number of hours has to sum to a maximum of 10. So Alex isn't going to work for more than 10 hours a day on either fishing or shirt making. So that border of that feasible set is the feasible number of hours that he could spend working on fish or on shirt making. Now he could hypothetically spend less time on each, say, 2 hours and 2 hours, summing to a total of 4 hours. But that would not be on the border of his feasible production set. So on the border of the production set over here, he's always spending 10 hours, but the number of hours is just varying between the two different production activities. So as we say here, he can work for a total of 10 hours each day. Labor constraint, he can't put in more hours of labor beyond this time. Okay, so at point D over here, he spends 5 hours on fishing and 5 hours on shirt making. Now recall, that resulted in 2.5 fish and 2.5 shirts. Okay, so let's start putting these together. We are going to use what we call a four-quadrant diagram here. And with this four-quadrant diagram, we're going to start with this part over here, which is exactly the same figure we looked at a second ago, just flipped over. So we flipped over that figure. We've got the labor for shirts on the x-axis. We've got the labor for fish on the vertical axis. And so what you want to think of here is that this is 0 hours spent on either of those activities. Over here, we're spending 10 hours on producing shirts. Over here, we're spending 10 hours on producing fish. Okay, but do we know yet how many fish and shirts we'd have? Well, no, we don't know yet. In order to do that, we're going to have to add our production functions. But just as a reminder, if we're at point D, what are we doing? We're spending 5 hours using shirts and 5 hours for fish. Okay, Now we've added the production functions for fish and shirt making. We have economies of scale over here in shirt making. We have constant returns to scale in fish production, or the agricultural activity that we could engage in. And what we can see here is if we spend all our time, 10 hours, at point C on our fish production, we'd have 5 fish. If, on the other hand, we moved away from 10 hours of fish and we had 0 hours spent on fish, what would that mean? If we've moved along the feasible allocation of labor, we would then spend 10 hours on shirt making. Therefore, we would be at point A and we would be producing 10 shirts. Now, this is going to tell us how we can get to our production possibilities frontier. So the first thing to think about is that we've got point D, where we've got 5 hours spent on fishing and 5 hours on labor. So on labor for shirts. So we've got 5 hours for each of them from point D. That means we're at point E on the shirt production function, where we can get 2.5 shirts, and we're on F on the fish production function, which means we get 2.5 fish. So with both of those points, we also then immediately get a mapping to our production possibilities frontier. So here we have superimposed the production possibilities frontier. At point B, what happens? We have 2.5 fish and 2.5 shirts. At point A from our shirt making, what do? We go all along, no time spent on fish production, and we get 10 shirts. Or if we spend no time on shirts, we've got 0 time spent on shirts, but we've got 10 hours spent on fish, we'd end up with 5 fish. So as we spend time on the different activities, on fish or shirt production, we're going to move along that production possibilities frontier, and that's because we're moving along our feasible number of hours that we're allocating to the different activities. We're going to spend 10 hours either on fish production or on shirt production, and then when we allocate our time to these different activities, we're going to be mapping out the production possibilities frontier. So with all 4 graphs, we can look at, say, point D, see with point D, like I already said, that there are corresponding points, point E with shirt production and point F with fish production. Then those 2 points correspond to point B on the production possibilities frontier. And so that is telling us how we get from a point on the feasible set of labor time to the points on the production functions to the point on the production possibilities frontier. And so with this production possibilities frontier, he will produce at, say, point B, where the output is 2.5 shirts and 2.5 fish. Now, here's the thing. We don't yet have Alex's preferences. All we have mapped here is what his production possibilities frontier looks like. This will then give us the marginal rate of transformation. Remember that the marginal rate of transformation is the negative of the slope of the feasible frontier. Here, it would be the negative of the slope of the production possibilities frontier, or the PPF. So that would then give us the MRT. We do not yet have the marginal rate of substitution, which is the negative of the slope of the indifference curve. It's once those 2 things are equal to each other that we can find the point at which Alex would produce, given his feasible choices between fish and shirts. So, just a reminder, the PPF with economies of scale shown is going to be convex to the origin. Now, why is that? That's because there are economies of scale in shirt production. So, with economies of scale in shirt production, this PPF probably looks quite different to PPFs you might have seen before. We looked at a feasible frontier in chapter 3, where I'm just sketching it here. We had 2 variables, x and y, and it was concave to the origin. This production possibilities frontier, or feasible frontier, pardon me, this production possibilities frontier is convex to the origin. What are we seeing here? That's a consequence of the economies of scale in shirt production. And so When we think about the negative of the slope of the production possibilities frontier, showing the opportunity cost of acquiring more fish by shifting labor between the two activities, what we're going to see is that there's going to be what? A change in the opportunity cost that looks different to what we saw in the production possibilities frontier or the feasible frontier that we had in chapter 3. And so that's going to affect the utility maximizing choice that Alex is going to engage in when we include his indifference curves.